The Robot Operating System, or ROS, is an open-source framework designed to help developers build robust, complex robotics systems. It is not a true operating system like Windows or Linux. Rather, it is a middleware that sits between your underlying operating system and the robot application code. It's a collection of software tools, libraries, and messaging systems that help break robot code into manageable chunks called nodes. Additionally, it contains a wide array of debugging and simulation tools that help you design and test your robot code. In this 12-part series, I'll help you get started writing ROS applications. Specifically, we'll cover ROS 2, as that is the current version recommended for new projects. Let's take a look at what we'll cover. In this video, we'll go over a brief history of ROS and why it's useful for robotics projects. I'll talk about the two major supported programming languages, Python and C++, and when you should consider using each. We'll look at the differences between ROS 1 and ROS 2, as well as explore some of the downsides of ROS in general. Finally, I'll mention some alternatives to ROS and give you examples of where ROS has been used in the real world. We won't actually use ROS in this episode, as that's saved for the next episode. Because ROS is tightly coupled to an operating system, usually Ubuntu, I'll give you a Docker image that has everything pre-installed. We'll run that and explore some of the basic command line tools in ROS to help you get a feeling for navigating and debugging a project. Next, we'll dive into publishing and subscribing to topics with Python, followed by doing the same in C++. Sometimes the publish-subscribe model does not work, and you need something to process requests. This is where services come in, and we'll explore that in Python as well as C++. Both topics and services rely on strict typing given by interface definitions. While ROS comes with a number of such interfaces, we'll look at how to create our own interfaces. In many cases, you'll need to start nodes with different parameters, so I'll demonstrate how to set up and use ROS-style parameters. Then we'll examine creating custom launch files so you can run multiple nodes with a single command. At this point, we will have covered all of the basic functionality of ROS. This should be enough for you to create packages with multiple nodes and custom interfaces. In the last 3 episodes, we'll tackle some more advanced concepts. Specifically, we'll talk about the TF2 library used to create transforms between frames. TF2 can be a little tricky, so we'll take 2 episodes to tackle it. Note that I'm only going to use Python here, but I'll provide a C++ example in the course's GitHub repository should you want to see it. In the first episode, we'll talk about why you might need TF2, introduce TurtleSim, and create a simple broadcaster. In the second episode, we'll dive into TF2 broadcasters and listeners, and I'll issue you a challenge to create a train of turtles in TurtleSim. This will test your knowledge of the concepts up to that point and serve as a fun demo project. Finally, we'll discuss interfacing with microcontroller units, or MCUs. Up till now, you might have noticed that we have not talked about anything usually associated with robots, motors, servos, sensors, and the like. That's because ROS is primarily a multi-processing messaging middleware. It's pure software intended to run on a general-purpose operating system. As you'll see, ROS is meant for large, complex robots. It's up to you, the developer, to figure out how to connect actual hardware. In many cases, ROS-based robots will have one or more full computers running ROS to handle the complex calculations, like vision processing or sensor fusion. The computers will communicate with off-board microcontrollers that handle the low-level processing, like reading from actual sensors or controlling motors. Micro-ROS is a newer project to the scene. It is a lightweight version of ROS designed for microcontrollers. It integrates with real-time operating systems like FreeRTOS and Zephyr. As a result, you still need a fairly powerful microcontroller with a good amount of RAM to run micro-ROS. Also, it's still actively evolving and has support for only a handful of boards. Micro-ROS is a fairly complex beast. which would require its own video series, so we won't get into it here. If your microcontroller needs are simple enough, like reading a few sensors or controlling a couple of motors, you can get away with a simple messaging scheme over UART or SPI. And that's exactly what we do in this finished robot demo. The Raspberry Pi runs ROS and OpenCV to find the ball in the frame and then sends continuous messages to the Pi Pico board, which directly controls the motors. We'll talk more about how this is done at the end of the series, but first, let's look at how ROS came to be. ROS began life as a project idea by two Stanford PhD students, Eric Berger and Keenan Weiroback. While working on personal helper robots in the robotics laboratory, they noticed that up until that time, a lot of robotics research effort was spent reinventing the proverbial wheel, especially in software. So they proposed an open source software framework that could be used in a variety of situations and on a variety of hardware. In essence, a Linux for robotics. The next year, Scott Hassan, the founder of the robotics incubator Willow Garage, took an interest in Berger and Weiroback's work and invited them into the Willow Garage program. In 2008, the team achieved a few major milestones. First, they proved basic navigation and door manipulation with the PR2, the hardware prototype they had been building, which ran ROS version 0.4. They also published the first paper on ROS that year. A couple of years later, in 2010, ROS version 1.0 was released. Then, in 2012, Willow Garage created the Open Source Robotics Foundation, or OSRF, who are now the official maintainers of ROS. That was also the first year of the ROSCon conference, and the release of the first commercial robot that ran ROS, named Baxter. A couple of years later, Willow Garage was shut down. Its assets and most of the employees are absorbed into one of Scott Hassan's other companies, Suitable Technologies. Then, in 2017, OSRF changed its name to Open Robotics, and ROS2 is released. The collective developer team recognized the architectural limitations in the original ROS and rewrote most of the framework to better support the needs of industrial robotics. In ROS 1, node discovery and coordination relied on a central system called the ROS master. ROS 2 replaces that with the Data Distribution Service, or DDS, which is a decentralized system that handles both node discovery and messaging without needing a central server. This makes ROS 2 much more scalable and robust. You don't need to worry about these details. It all happens under the hood. But it's why ROS 2 had to be rewritten from the ground up, rather than just being a version upgrade from ROS 1. By the time this video comes out, ROS 1 will have reached end of life, which means no new updates, fixes, or support. As a result, we will stick with ROS 2 for this series. In ROS, the fundamental software building block is called a node. This is a process that performs some task, like reading data from a sensor or controlling motors. Nodes are usually implemented as subclasses that inherit from the ROS node class. This structure encourages good use of object-oriented programming principles like encapsulation and abstraction. In most cases, each node is written in its own file, commonly using Python or C++. While you can define multiple nodes in a single file, which might save on some overhead, ROS encourages splitting nodes into separate files to improve readability, debugging, and reusability. When you run a ROS application, each node typically runs in its own process and runtime environment. Nodes can communicate with each other using a few methods. The first are topics. These are named communication channels used for the publish-subscribe model. Nodes can subscribe to one or more topics, and whenever a message is published to that topic, all subscribing nodes will receive it. For example, you might have a sensor node that regularly publishes data and a driver node that uses the information to avoid obstacles. Another option is the service. This is a synchronous communication method where a client will send a request to a server and the server is expected to reply with a response. Requests and responses are specific types of messages. All messages, including those used for topics, contain one or more fields with strongly typed data. These might be strings, integers, floating point numbers, arrays, and so on. Each message must be defined by an interface. This is the format of the message, a description of what kind of data the message should contain. Think of it like a programming API. It defines what kind of data is expected to be received or sent by a node, whether in a topic or a service. ROS comes with a number of predefined interfaces, but you can also define your own. Note that nodes can instantiate one or more of these messaging types. Each node can have multiple publishers, subscribers, clients, and servers in it. One of the many benefits of ROS is that nodes can be written in almost any programming language. While ROS officially supports Python and C++, the community has added support for JavaScript, Rust, Go, and others. Any node can talk to any other node, as each node ideally runs in its own runtime environment and adheres to the interfaces defined for a particular topic and service. If you head to docs.ros.org, you can find documentation for all the various ROS distributions. Jazzy Jalisco is the latest version when I recorded this series, so we'll be using that. Click on the documentation link. Here you can find information about ROS, this particular distribution, concepts, tutorials, and API. First, click on Distributions. Here is a list of all the ROS 2 distributions. As you can see, the ROS development team likes to keep a cadence of one major release per year. Also, note that every other release is a long-term support version, similar to how Ubuntu does releases. Jazzy should be supported until 2029, so we're safe to use it for now. That is, unless, of course, you're watching this after 2029. In that case, I recommend using whatever the latest long-term support version is and making any required changes to the function calls. If you click on the Jazzy Jalisco link and scroll down, you can see the supported platforms. ROS is more than just a software middleware. It contains a number of tools that are tightly bound to a particular operating system. While Windows and Mac OS do get some support, in general, your best bet is to use the exact version of Linux listed under the Tier 1 section. This will usually be the latest long-term support version of Ubuntu, which is 24.04 for Jazzy. You're welcome to try another operating system, but you can expect to fight with dependencies and versions during the installation process. Click on the install link and click on the deb package link under Ubuntu. This doc very nicely lists out the steps required to install ROS 2 on Ubuntu. If you have Ubuntu 24.04 installed or don't mind using a virtual machine or container, feel free to follow these steps manually. In this series, I'll use a Docker image that has already performed these installation steps so that you can have a similar experience on just about any host operating system. You'll just need to install Docker Desktop. Now, in the sidebar, click Concepts, Basic Concepts, and Client Libraries. Here you can read about the two main libraries that ROS provides, RCL-CPP and RCL-Pi. RCL stands for ROS Client Library. The core RCL is written in C, and the C++ and Python libraries call into this core RCL. When you want to define a custom node or interact with topics, services, or parameters, you'll typically start by importing one of these libraries. As you can see, ROS officially supports two languages with these client libraries, C++ and Python. They implement similar functionality in their respective languages, and as a result, they have similar APIs. Scroll down and you can see a list of community-supported languages that ROS 2 recognizes, but the core dev team does not actively help maintain. The community has RCL versions in Ada, C, Java, .NET Core, Node.js, Rust, as well as Flutter and Dart. Like with any community project, support for such languages may drop unexpectedly, so I would use these with caution. In this course, I'll demonstrate most concepts in both Python and C++. I'll usually show something first in Python as I find it's a little easier to read and most beginner programmers have some familiarity with it. Then I'll demonstrate the same concept in C++, which often has a little more difficult syntax to read. To effectively follow this course, you should be familiar with either Python or C++. If you know both, that's even better. You should have a pretty good grasp of object-oriented programming principles like encapsulation, abstraction, and inheritance. Every node we create will be a subclass of the main RCL node class. You should also know how callback functions work. If you decide to work in C++, ROS makes heavy use of modern C++ concepts like templates and smart pointers. I recommend brushing up on those concepts if you need a refresher. You will also need to know some basic Linux command line functions like running executables and working with paths. This question often comes up in the ROS world. Should you develop your application in Python or C++? The reality is that they are different tools for different jobs. Python is often considered easier to learn and write, which makes it great for quickly prototyping ideas. Part of this ease comes from dynamic typing, where variable types are figured out at runtime instead of during the build stage. Another advantage is that most of the machine learning community uses Python, which opens up a ton of possibilities thanks to the vast array of available AI and machine learning Python packages out there. All of this comes at a cost, however. Python is generally considered much slower than C or C++, as it is usually executed through an interpreter. You can expect Python programs to run about 10 to 100 times slower than something similar written in C++. The interpreter and various layers of abstraction also introduce memory overhead. In ROS2, each node usually runs in its own runtime environment. This means every Python node needs to spin up its own interpreter, which consumes more memory than running a compiled C++ node. The default Python interpreter, CPython, includes a feature called the global interpreter lock, which prevents true multithreading, thus limiting parallel execution for CPU-bound operations. Future versions of Python might make this optional, but it's still a constraint you have to deal with for now. C++, on the other hand, is generally more performant than Python, as it is a compiled language. It also offers you low-level control, as you can more easily manipulate individual bits in memory. It offers compile time type checking, which helps prevent errors during runtime. As a result, C++ is usually better when you need fast response times for real-time applications, like responding to sensor input within a few microseconds. However, the C++ syntax is more verbose and complex than Python, which can make it trickier to learn and slow down development time. Remember that you can mix and match languages, so you could have a Python node that uses complex vision processing packages to send coordinates to a C++ node that handles low-level functions like motor control. You could also prototype nodes in Python and then rewrite them in C++ for better performance when you get closer to deployment. While ROS is incredibly powerful, it does have a few limitations. It abstracts a lot of functionality and offers a lot of tools that can be overwhelming for newcomers. It also introduces some overhead, as each node runs in its own environment, and the underlying DDS system can introduce some latency. Because ROS ties closely into the underlying operating system, you can sometimes find yourself wrestling with dependency versions just to get everything working. For that reason, ROS isn't always the best fit for small, low-complexity projects or when you're working with low-power microcontrollers and need to meet tight real-time deadlines. While micro-ROS exists to help with this last part, it's not something we'll cover in this series. Other robotics-focused middleware frameworks do exist, like the Open Robot Control Software or ROS project, or the Lightweight Communications and Marshalling project. In some cases, you will find robot manufacturers building their own middleware or skipping this step completely for simpler designs. But ROS really is the industry standard these days, especially for prototyping. For example, Vecna uses the navigation stack in ROS for many of its autonomous warehouse robots. Omron uses the ROS MoveIt package for its TM manipulator arm. And NVIDIA maintains Isaac ROS, which is a collection of packages built on ROS2 that run efficiently on NVIDIA GPUs. There are many other examples, so you can rest assured that your ROS skills will be valued in the industry. At the end of the course, I'll demonstrate connecting ROS to real hardware. This is the XRP platform. The Raspberry Pi runs Ubuntu, and OpenCV grabs and processes images from the camera. This is done inside a ROS node that sends those results to another node that sends driving directions over USB to the RP2350 underneath. That, in turn, directly controls the motors. The robot looks for blue blobs and tries to drive toward the largest blue object. It attempts to maintain a particular distance by having that blob be a certain width in the framework. This gives me a fun, interactive way to control the robot with something like a ball. I hope this gives you a decent overview of what ROS is and why you might want to consider using it. Let's see how to build and use the Docker image for the course so that you can start developing ROS applications. If you are on Windows, you will want to install the Windows Subsystem for Linux, or WSL. Open a terminal in administrator mode and enter WSL-install. That will give you a Linux backend for Docker, which we'll need going forward. Head to docker.com and click on Products, Docker Desktop. Scroll down, click on Download Docker Desktop and choose your operating system. Run the installer and follow the on-screen instructions. Open the Docker Desktop application. You will need this running anytime you want to run a Docker image for this course. If you are on Windows, click on the Settings button and scroll down in General. Make sure that the WSL2 based engine option is selected. Head to github.com/seanhemel/introduction to ROS. From there, go to Code and download the zip file that contains this entire repository. Once that's done, unzip it somewhere on your computer. Make sure that Docker Desktop is running, and then navigate into the Introduction to ROS folder that you just unzipped inside of a command line prompt. In there, you should see a Docker file. So we're going to build the Docker image using docker build-t, env-ros2, that's the name of the image. And then don't forget the period at the end to give Docker the context of this folder for where we want to build. That's how it finds the Docker file. Wait a moment while that builds. When that's done, we will run the image, so call docker run --rm. RM deletes the container whenever we're done with it and we shut down the container. This keeps everything in that container nice and neat. You're welcome to run this without RM, but I like keeping things neat. As you'll see, we will mount a workspace so we can keep our work on the host machine as well, that we don't lose any work. -IT means interactive mode so that we can debug it if needed. -E, we will pass in an environment variable. The webtop image that this is based on likes to have PUID and PGID set as environment variables, so it knows what to use for the user and group IDs inside of the container. We're going to pass in our host system's ID, which allows us to read and write files in that workspace. It makes it a little easier. If you're on Linux or Mac OS, you will want to set PUID to $ and in parentheses ID-U. This runs the ID command for the user, gets that ID and passes it in as the PUID environment variable. If you were on Windows, make sure you're running in PowerShell, and we're going to use the command WSL ID-U, which kind of does the same thing. It gives the user ID for the Windows subsystem for Linux. Similarly, we want to pass in the group ID, so -E, then PGID equals $, and if you're on Linux or Mac OS, this is ID-G inside those parentheses. But if you're on Windows, inside PowerShell, use PGID equals $, and in parentheses, WSL ID-G. We'll expose the port 22002 that maps to port 22 in the container. This exposes SSH, should you want to SSH into this container. Webtop broadcasts as server on port 3000. We're just going to map that to port 3000 on our host machine so we can access that Linux GUI environment using a web browser. Next, we'll mount our workspace volume. This should be the current working directory, so $ in curly braces pwd /workspace, then :/config/workspace. Webtop likes to mount things to config. It considers that the home directory. In Linux or Mac OS, this should work, but if you are in Windows, you will want to do this from PowerShell. Next, we will give the name of the image that we just created. This is env-ros2. Hopefully that fires up without any errors. You can look through these. Some of these errors and warnings you can ignore. Like this one you can ignore, and these warnings you can ignore. As long as you get to this step where it prints out this number here, you should be good. In a web browser, navigate to localhost :3000. This will connect to the webtop server that's running in our Docker container. When you first log in, you might see these CASM VNC controls show up. That's part of the broadcast VNC desktop environment. We won't need them for now, so you can just minimize them by clicking this arrow. But if you need them again, click the arrow on the side. We're just going to test to see if ROS 2 is installed correctly and runs. So at the bottom, click on Terminal Emulator. If you're curious, take a look at the home directories .bash rc. You can see that inside of this image, this Docker image, we have already set up this source opt ROS Jazzy setup.bash. That configures and launches the ROS 2 environment in our shell to give us access to the ROS 2 tools that we will be using. These are the command line tools. If you were installing ROS 2 locally, feel free to add that line to .bash rc, or you will need to manually source that setup.bash script. So I will call source opt ROS Jazzy setup.bash. Now I have the environment loaded in this particular terminal instance, and I can use the ROS 2 commands. So I can type ROS 2. If I press tab a few times, you can see the variety of tools that I can launch from within the ROS 2 meta tool. To test, we're going to say ROS 2 run. There is a package called demo nodes, and then you have the option of CPP or Pi. So we're going to do Pi here. If I push tab a couple of times, you can see the options of executables within that package that I can run. We're going to call talker here, and that's going to fire up a ROS node that's just publishing hello world to the terminal. Let's open up a new window. It should automatically source setup.bash from the ROS instance. If not, you will need to manually call it in your new terminal because every session is different. And we will call the listener executable that's in the demo nodes Pi package, like we did with the talker, but this time it runs a listener node that subscribes to the talker, and you should see it printing out the exact same message that's being broadcast from the talker node. If you see this, you know that ROS is correctly working and correctly installed on your system. When you're done, close out of these terminals. You can press Control-C to stop the node if you wish. Something I've noticed about WebTop is that you can't really shut it down from the terminal instance that's running the Docker container. So here's that container running. If I press Control-C, nothing happens. Control-X, also nothing happens. There are some processes that are running in the background that prevent capturing this signal and doing something like shutting down the image. There are a few ways you can shut down the image. The first is to just exit out of the tab or the terminal that you're working with on your host machine. Another thing you can do is in Docker Desktop, the GUI, go to Containers. You can click the Stop button here, and that will stop the container. Remember that everything inside gets deleted except for that workspace folder you mounted. And you can find that folder in the unzipped Introduction to ROS folder where we created this image and launched the container from. The other thing you can do is open up a new terminal on your host machine. You can do Docker PS. We're going to list out our processes. And you can do Docker stop and get that container ID. So I'm going to copy that and paste it there, and that will stop the container. If you go back and look at your browser, you can see that the VNC is no longer running because we stopped a container, which means everything has stopped appropriately. In the next episode, we'll explore the ROS 2 command line options even more so you can get a sense of how topics and services work. Using these tools is crucial for testing and debugging your nodes. After that, we'll dive into actually writing code for custom nodes. Stay tuned.